All right here, folks. I need you guys to stop talking, please. So I'm going to run through the solutions from this assignment from last time real quick. So make sure that you have your stuff out and you're checking your papers. So I have there's the tables and the domains and ranges, and then down there to the right, pretty small, is my picture.
I asked myself that.
Okay. I'll give you guys a minute here to look at this and kind of check things over. Then I'm going to scroll to the next one. So let's look at 2. Okay, let's go on to 3. And we'll take questions here at the end, so just kind of, do some checking of your own. Double check what you're doing, and if you have questions about whatever, we can do some examples at the end. But this is, come test time or whatever, this is an appropriate amount of work, what I've shown right here. You don't really need to show a whole lot. So here's 4, and I guess you can see 5 there at the bottom also. Not the picture for 5. I guess in hindsight I should have done 2 colors for these pictures so you could see the graph and the axis a little better. But that's 4 and 5. Yeah, the cube root. Yes, for all cube root functions, the domain and ranges are all the same. That is correct. So that's a good question, a nice observation. You definitely would want to remember that. That makes life quite easy to deal with. And we'll scroll down a little bit more. So here's 5 and 6. You hate what? Okay. And then the last graph here at the bottom would have looked like that. Okay. Do we want to run through any of these here? Ask any question? Jack? Correct. Yeah, so Jack is asking about like 1 and 4. Notice on problems number 1 and number 4, there's no number in front of the radical. So in that case, you assume that the A is 1. So the A is the coefficient in front, and we know if there's no coefficient shown, that it's a 1. So same thing for number 1. The A there would have been 1. Okay. Is there any of these you'd like to see done? All right, fair enough. So we'll move on today. And over the next couple of days, we're going to be talking about simplifying expressions with radicals. So we have two important properties that we're going to be using primarily to deal with these sorts of problems. The first one is called the product property. So what this property is saying is if I want to multiply two radicals together, they must be the same kind of radical. So in this case, notice that both our radicals are cube roots. And if they are the same kind of radical, we can just multiply the radicals together by multiplying the radicands together. So in this case, the cube root of 7 times the cube root of 10 would be the cube root of 70.
What happens if they reject?
We'll deal with that later. That won't be a today question, but we will deal with that. And that's a reasonable question to ask, because certainly that could happen. But we need to kind of extend our definition of what we mean by a radical in order to kind of answer that question. So that wouldn't be something that we're going to talk about today, but we will. The next property that we're going to talk about is called the quotient property. And what the quotient property is saying is if I have two radicals with the same index, if I divide them, that's the same as dividing the radicands. So for example, if I have the fourth root of 10 over the fourth root of 25, I can treat that as the fourth root of 10 over 25. And I can reduce the fraction 10 over 25, right? What does that reduce down to? 2 over 5. Is everybody okay with that idea? So these are two important properties that we're going to use to simplify radical expressions. Okay? But there's some other things that aren't quite properties, but are kind of useful ways of thinking about these problems, or conventions in terms of how we're going to represent an answer that are really important that I'd like to take some time to talk about. So when we want to simplify a radical expression, our final answer should have the following attributes. So if we have multiple radicals in our problem, ideally they should be combined into a single radical if possible. All radicals are reduced. Oops. And then we don't have any radicals in the denominator of a fraction. So the tool that we're going to use to combine our radicals is going to be the product and quotient properties. But these other two steps, we need to spend some time kind of talking about them. Specifically, I would like to start with talking about how do we reduce a radical. Okay? So before we address this, imagine we're going to the bank. Okay? And we have 13 quarters. We want to take that 13 quarters to the bank. Yes. We want to take these 13 quarters to the bank and exchange them for a bigger denomination, like dollar bills. So if I take these 13 quarters to the bank, what are they going to give me back?
Oh, wait, oh, never mind. Never mind. $3. I thought you were talking about dollars. That's $1.
Everybody agree with that? Why are we getting back? Why did we get this much back from the bank?
Because we exchanged it.
Because each dollar bill is 4 quarters. 4 plus 4 plus 4 is 12. And plus one more quarter is 13. Everybody okay with that idea? Okay. What if we have, I don't know, like 37 dimes. What are we getting back here? $7.10?
No, that's dimes. $3. No, it's not 10. Oh my god. Wait, $3. $3. Yeah, that. You know what? I could have done it.
$3 and not 7 cents, 7 dimes. So I'm gonna get $3 bills and 7 dimes back, right? Okay. All right. So if we think about the square root of 3 to the 5th in the same way, what's going to happen here?
37 cents. What? Even
one going into 3.
So what is the exchange rate here between things under the radical and things outside the radical?
5.
So the exchange rate is the index for the radical. For a square root, what is the index? It's not 1. 2. No, you need to keep trying. It's okay to say things that are wrong. That's how you learn, like, whether what you know is correct or not. It's okay to make mistakes. Okay? So, stop talking, please. So, it takes 2 3s underneath the radical to get 1 3 outside of the radical. So if I do that exchange once, I'd have this, right? I took 2 of the 3s from underneath the radical and exchanged them to get 1 3 outside of the radical.
Oh, and you just have to add a number on the outside.
Just like if I went to the bank, I can take 4 quarters and turn it into a $1 bill.
Yes.
Do we see the similarity there?
Yes. That don't look like quarters.
Can I do that more than one time?
Yes.
Can I do that again?
Yes.
Yes, because I still have 3 3s.
Why are we taking the 3 out?
This is exchange rate.
I actually think it's limited.
Yeah.
This is making sense in my head. Yeah.
Okay. The way, stop talking, please. Stop talking, please. What we're trying to do is we're trying to think about this problem the same way we would do an exchange rate. Okay? So what we have is we have 5 of the 3s under the radical. Right? That's what this is showing me right here. Do we see that? 3 to the 5th means I have 3 times 3 times 3 times 3 times 3. So I have 5 3s underneath my radical. Does everybody agree with that? Now, the 2 tells me the exchange rate, that I can take 2 3s from underneath the radical and trade them in for 1 3 outside of the radical. That's what I've done the first step here. You'll notice underneath the radical, how many 3s do we have now? 3 of them. How many 3s do I have outside of the radical? 1, because I took 2 of the 3s from underneath the radical and traded them in to get the 1 3 outside of the radical. Okay? Just like if I went to the bank with 9 quarters, I could trade 4 of them in to get a dollar bill back. Could I trade another 4 in? Yes. Can we trade another 2 3s in? Yes, because the exponent underneath my radical is still greater than the exchange rate.
Oh.
So I did it a second time to get a second 3. That leaves me with 1 3 left over. Don't I need to square that?
And I get it now. So as long as the exponent is bigger than the radical, you can keep taking it out?
Yes.
Okay.
So this then we would call 9 square root 3. This is our reduced radical.
Wait, we're not into the 2. I don't want to.
We don't need to write it there for a square root. I just wrote it in to kind of illustrate to us what the exchange rate was. Tom?
You just went from having 5 3s to now we're having 3 3s.
No. We had 5 square roots of 3.
Okay.
Now we have 2 regular 3s and 1 square root of 3.
And we get the square root of 3 because of the 2 outside of the 3.
The square root of 3 is left over because we've exchanged. We had 5 square roots of 3 to exchange. We exchanged 2 of them to get this 3 outside of the radical. We exchanged another 2 to get the second 3 outside the radical, leaving us with just 1 3 left. So these 3s out here are like our dollar bills. This 3 underneath is like our leftover quarter. Does that feel okay? Josie. So the 2 is the index on the square root. Do we need to write a 2 when we write the square root symbol? No, I wrote it there to kind of illustrate, to remind us what the exchange rate is going on here. But you don't need to include that for square roots. Any other radical, though, that number needs to be there the entire time. Let's try another. Sound okay? Let's do this. So here we have the cube root of 2 to the 14th. What is the exchange rate here? 3. Okay. How many exchanges can I do of the 14 square roots of 2?
4.
I can take 4 of them out. If I do 4 exchanges, how many square roots of 2 are then left? 2. So we'd say that the reduced radical here is 16 cube root of 4. Notice here, the people that answered it quite quickly, what they did is they divided 14 by 3. So the 4 told us how many 2's we could take out, and the remainder told us how many 2's would be left over. Right?
Did you know I did that?
How did I know you did that? Because of how quickly you answered. Is that you're doing this process or ostensibly doing this process? If it took you like just a second to answer the question, which is the way you'd want to think about it. It's the best way to think about it. It's fast. Let's do another. Is this starting to feel familiar?
Yeah.
It's like better.
So we have the 5th root of 7 to the 12th. So what's the exchange rate here? 5. Okay. How many 7s can we take out? Everybody agree with 2? Because 12 divided by 5 is 2. And what's the remainder? 2. So this would be 7 squared times the 5th root of 7 squared. This 2 is that 2. This 2 is that 2. That's all we're doing. It's like a elementary school division problem that we're turning this problem into.
Wait.
Yes, Sophia.
So all of this is just to simplify it?
Yeah. We're just talking about how to reduce the radical in a way that's like, I'm trying to make this really familiar and something like making an analogy that should feel comfortable.
But all we're doing is, like, we're doing this to simplify it.
Yeah. This is part of the simplification process, is we need to make sure our radicals are reduced.
Can I get a good O?
Can I what?
Oh.
It is being recorded. How about this one? We have the cube root of 2 to the 22nd. How many 2's can we exchange here? 7. So we have a 2 to the 7th. And how many are left over? 1. It is not bad. So we feeling a bit better here? Okay. It is possible. We're just going to need to rewrite 48 in a different form.
Divide 3 by 22, so that's 7. Remainder 1. Because 3 goes into 27, 27 times 21. So then you get to 7
That sounds right. What if instead of writing it as 48, we did a prime factorization, write this as 2 to the 4th times 3?
Yeah.
Because we didn't have it written in an exponential form to where we can exchange rate. Right? It's just like you had a big pile of money and you didn't know how many quarters and nickels and dimes or dollar bills or whatever you had. You had to sort them out into each denomination. So when you go to the bank, you can make an exchange, right? What is the exchange rate on this problem? It's 2. How did you know that? It's a square root, right? If there's no index written, we know the index is 2. So how many of the 2's can we trade in? We can trade all of them in and get 2 2's coming out, right? Well, we have 4 2's, and the exchange rate is 2.
Yes. Wait. How did we figure that one?
Wait.
Oh my God, that's what I said.
Right? Because there's no 2's left.
How do you know that the exchange rate is 2?
Square root.
Oh, so it's always 2.
For a
number.
Exactly.
Oh, yeah.
Yep. And can we do anything with the 3?
No.
No, because there's just one of them. What's anything to the 0 power? 1. So this would be 4 square root 3. Let's do another. Let's say we want to do the cube root of 80. What do we need to start doing? Yeah, we need to do the prime factorization of 80. Why don't you try to do that on your sheet of paper now in front of you? This is something that you should be able to do by hand without taking a ton of time. Is that what you guys got? Let's just illustrate. So I have 1, 2, 3, 4 2's and a 5. Right? Okay. So let's do our exchanges. What do we get here? What can come out? 1, 2. What's left underneath? 1, 2, and 1, 5. Let's try the square root of 72. Is that the prime factorization you guys got for 72? Should be able to do that. I'm not always going to be able to do it for you. Annalise? Correct. Because it's multiplication, absolutely. The exponents need to be on the correct number, but like you can't have 2 squared and 3 to the third. But the order, whether you put the base 2 first or base 3 first, doesn't matter. Then you're done. There's nothing to do. That's okay. All right, so what can we take out of here? What comes out of this radical? 1, 2, and 1, 3. Okay, what's left? Okay, or you could just write it as that. Is everybody okay there? Okay. What if we have the cube root of 16 times the cube root of 28? Great. What's the prime factorization for 16? Good. And what's the prime factorization for 28? Anybody? 3. 2 squared times 7. Right? Okay. Now what should we do? I want to point out these have the same index. So what can we do here? I can do the product property and write this as that. Everybody's okay there? And what is 2 squared and 2 to the 4th? Can I combine those? Because they're both 2's. How many total 2's would I have? 6 of them. Okay. So now we're ready to do our exchange. So what would my final answer here be? You mean cube root 7. Okay, instead of writing 2 to the 2nd, though, I'm going to write 4. How's that? Okay. Let's do some more. What should we do first? Okay, what's the prime factorization of 75?
That's a good question. I'll figure that out. Wait, so prime factorization is that
You just draw the factoring tree like we did up here.
So is it just 5 times fraction times 2?
Okay. Elena, you can do that prime factorization really any way you want. You just need two numbers that multiply to that one, and you just keep breaking the numbers down until they're primes. It doesn't really matter how you do your splitting. You should get the same answer either way. Okay. And now let's do the prime factorization of 24.
2 to the third times
2 to the third times 3. Notice now that both of these are the same index of radical, right? They're both square roots. So what can we do? Combine them using the quotient property. And then what do you notice about this fraction? The 3's cancel out. Exactly right. Very good. Okay. And now we should do our exchange, right? Okay. So what can come out? What comes out again? I heard a lot of 1, 5, and 1, 2 is not quite right. So you have a 5 to the first, because that 5 is in the numerator, and a 1 over 2, because that 2 is in the denominator. Everybody okay there? Look at where the 5 and the 2 are. Because I'm dealing with a fraction, the 5 needs to be in a numerator, and the 2 needs to be in a denominator. So that's the way I've written it, with 5 over 1 and 1 over 2. Okay? What's left inside my radical, though? Not nothing. 1 over 2. Why is there a 1 on top? It should be easy to see why there's a 2 in the bottom. Because really that's 5 to the 0. Up there, there's 0 5s left. And remember that 5 to the 0 is 1. Okay, with this? But these fraction ones, we still have a bit more to do. So we've done the reducing part, but I want to go back for a moment and remind you of this list of criteria we have. And I want to worry about this part now. Okay, no radicals in the denominator of a fraction. So if I go back to this problem we were in the midst of, I have the square root of 1/2, right? According to the quotient property, that's the same thing as the square root of 1 over the square root of 2. Everybody's okay there? Just use the quotient property to go the opposite direction, right? What's the square root of 1? 1. So really this is just 5 over 2 root 2. Everybody's okay there? And notice that I have a radical in the denominator of my fraction. Who remembers, probably from your geometry course last year, how to rectify this situation? You would have talked about this when you dealt with like the sine, cosine, tangent stuff.
Oh, that's cool.
That would be the most important or probably chapter of your geometry course, was that section. How about that? Multiply the top and bottom by the square root of 2. Why is that going to get rid of the 2 in the denominator? It doesn't cancel it out. What we have now is that, right?
Yeah.
Well, hold on, guys. I'm like way over explaining things because I want it to be clear kind of how I'm using these properties and speaking it all in the same language rather than creating the shortcuts around these things. Christina? Of course. Yes, Grace? We'll shorten this down here eventually. But I want to make sure that we understand what we're doing, because if you don't understand what the process is and why these things work, you're going to make mistakes on the shortcut and not realize that you made mistakes. It's really hard to tell if you get an answer that's nonsense, doesn't make any sense, if you don't understand like what you're shortcutting around, if that makes any sense. You know what I mean? Let's do another one of these. We'll do it a kind of the long way again, and then we'll start kind of trying to shorten up this process and not write down quite as many things. Okay? Oh, hold on a second. Don't want that. I want this. Sorry. So how many of you are ready to start dive into prime factorizations here? Can I make another suggestion? What if we do this first? Can that reduce? Let's do that then. Okay? What does this reduce down to? If you have to do more than one step, you can do more than one step. What's one thing that we can reduce out of here? Okay, we can take a factor of 2 out of each of them. Sure. And we can take another factor of 2 out, right? Okay. Can we do any more? No. So let's prime factorize this. This should be a little bit easier to do the prime factorizations for. You guys agree? This didn't work out the way I wanted it to. That's okay though. What's the prime factorization of 10? 2 times 5. What's the prime factorization of 27? 3 to the 3rd. 9's not prime, right? People that said 3 times 9, although that's the first step in your prime factorization. 9 isn't a prime number, so you'd have to keep going. Okay. Is there any exchanging we can do in the numerator? In the numerator, we have a 2 to the first and a 5 to the first. Is there any exchange that I can do in the numerator? No. How about the denominator? Yes. What can come out of the denominator? 1, 3. So because it's in the denominator, I have to make sure I write the 3 in a denominator. Okay. And then what's left in the denominator after I do that exchange? Just 1, yeah. So I'm not even going to bother to write it. So you can write it this way. Actually, let's not. That feels like we're going to get confused on what that means. Let's write it this way. Okay, that didn't work out the way I wanted it to because the denominator all the way reduced out of there. My apologies. Times 5 is 60. And I'm going to do this. Oops. Okay. First up, what should we do first? You could either do a prime factorization or you could try to reduce. I think here the prime factorization is probably just as easy as the reducing is, based on the size of these numbers, and there's no obvious divisors, right? What's the prime factorization of 160? Very good. 2 to the 5th times 5. What's the prime factorization of 567? Well, I created it that way. When I decided on 567, I did it by doing 3 to the 4th times 7. And I did that in my head. Do you know how to check if a number is divisible by 3? If the sum of the digits are divisible by 3, that number will be divisible by 3. So 5 plus 6 plus 7 is 18. And because 18 is divisible by 3, I know 567 would be divisible by 3. That's a nice prime factorization helper. Okay. So I guess we'll write them as a single radical. What can we exchange out from the numerator? One, 2. What can we exchange out from the denominator? A single 3. Notice I was careful to write them both in the numerator and denominator. So we're left with this, right? So So now to get rid of this fourth root of 7, what do I have to multiply the top and bottom of this by? How many 7s do I have in my radical right now? 1, right? To make an exchange, how many do I need to have? 4. So how many more 7s do I need? 3.
Back with the 2.